right?
Yes, we can. Thank you.
Okay, that's good. So let's get back to the problem 6 now. 1 second. Okay, now an I-shaped tension member is required to carry a load of 4,500 kilonewton, determined according to LRFD load combinations. The member end is connected using 2 gusset plates. These gusset plates are okay, we don't have to check them. We have to find the lightest HEA, HEB, or HEM sections of steel, given steel. Demonstrate that your member satisfies yield, fracture, and block shear. So we have 3 things here we have to care about. And we have to assume plates are okay, gusset plates. And also compare the weight of sections. So here we are given also that the the bolts are 22 in size. All right, so if we take a look here, we have 3 bolts on top and 3 bolts from the bottom. And also from this side, if we take a look here, we can see that we have 2 lines of bolts on top and 2 lines on the bottom. So in total, we have 12 bolts, 6 in the bottom and 6 on top. Now, after understanding the problem, we have to start with a section. Now, we are designing here, so we need actually to figure out which area we have to start with. So from the famous equation we know from the yielding of gross section here, 0.9 by the A gross multiplied by the yielding strength of the steel, we can find AG minimum if you manipulate this equation from here. Now you're given the load 4,500 and you already have the yielding strength. So given all this information, you plug them in. Now here you can see in my equation I have E plus 0.3. That means basically I'm just multiplying by 1,000. So this becomes 4,500 Newton, 4,500 multiplied by 1,000 in newtons. And we have everything else set. So from here, from this equation, I get my A gross minimum equal to 21,000 millimeters square. So this is the AG minimum that I have, and I have to pick a section from the sections table. So there has nothing to be less than this value. So when I go to the section tables in here, we are required to find either HEA, HEB, or HEM. So when you're looking and trying to pick a section, you will have to look at the areas in here. So according to what we found, 21.2, here we can start with this section. So basically the question is asking to try many sections actually. So to save time, I will basically show you one. I will show you HEM 300. So if we take HEM 300 and we take its gross area, now again, all the information, HEM 300. It's over here. So we can see that the gross area is equal to 303.1 centimeters square. If you multiply it by 100, it becomes millimeter square. So we have it in here, and we multiply and check for the gross yield at the beginning. So for the gross yield, as it appears, its capacity is 6,410 kilonewtons, which is bigger than what we need. That's good. Now we continue after checking the gross yield. We check the net rupture. So in the net rupture, again, we are using, according to LRFD, we have the factor of safety, FU, and the effective area. So first we have to find the effective area, which is equal to U multiplied by the net area. So at the beginning, what is U? U, we have to check from table D 3.1 in AISC. So if we go to this table and check for the shear lag, here we have case number 2. Since we have a wide flange, I-shaped, we will check for this one at the beginning. here we have this equation, 1 minus x bar over L. So we have it in here. And as you know, since the wide flange is connected from its flanges, it's connected from top, we have to cut it from half. So it becomes like a T-shaped member. Now we have to find the centroid, which is x in here, that is x bar. So from this equation, if you calculate only this side, you do not consider the gusset plates. If you cut the member HEM into 2 pieces and calculate the centroid, you will obtain 35.25 millimeters. And also, what about the length in here? So if we check about this, okay. So if we check from here, the connection from the last bolt to the first bolt, we have the distance here is 150. So that's why in my equation I have x bar divided by 150. Now we found the first U, but also we are not done yet. There is another U you can find. Well, since as you remember, we have 3 bolts to the inside and 3 bolts to the inside from here. We can see that in case 7 over here, this applies. And which one actually applies? With a flange connected with 3 or more fasteners per line in the direction of loading. So this is the case that applies for us. We have 3 bolts to the inside of the page in here in each line. Now we have to check whether BF is bigger than 2 over 3 the depth. So when you want to check for that, you want to go back to the sections table. Here we have the depth, and here we have BF, the flange width. So basically, you will plug them in these 2 equations and check which one actually satisfies. And you will pick either which one satisfies. You will pick your shear lag. So from here, it appears that BF is actually bigger than 2/3 D. This one's supposed to be up. D is supposed to be here. In any case, U will be equal to 0.9. So after we found U 0.77 and 0.9, which one are we supposed to take? We take the biggest one. Now we continue. We have the U. We have to find the net area. So for the net area, we are going to consider this shape in here, and the failure that we would expect in the net rupture would take place at this point in 2 bolts. So we are taking AG, the gross area at the beginning, minus the number of bolts. So first of all, this is the size of the bolt plus extra hole size to fit in. And you have here 4. Now, you might wonder, okay, we have 2 bolts in, that will be cut in. But actually, if you remember, we have 2 bolts from the top and 2 bolts from the bottom, from the wide flange. So in total, the cut, we will have 4 bolts, reducing the gross area. And also you have to remember your bolts are connected in the flange. So you're taking the thickness of the flange. So if we go back again and check from the section tables, HEM 300, the thickness of the flange is equal to 39 millimeters over here. That's why I multiply with 39. Now you plug in all of these in here, you would obtain your net area equal to 26,000. Okay, we multiply with the shear lag to obtain the effective area, and it becomes 23,000. Now finally, we check for the capacity of the member. Now in here, I have the reduction factor for the net rupture, 0.75 according to LRFD, multiplied by the capacity of the steel and rupture, and lastly multiplied by the effective area. So from here, we obtain the capacity of this member to be equal to 6,380 kilonewtons. Again, it's bigger than 4,500. That's good. So we're now satisfying 2 conditions, the gross yield, and we're satisfying the net rupture. Now the last check is the block shear. Now coming to the block shear, we have this equation provided to us from AISC. So in the AISC, where you can find this equation, let me show you. You can basically search, control find, block shear. Okay, not this way, let's try to block. So here is the equation, page 49. This is the equation that I'm using. Now, if you take a look at this equation, here is this line. Okay, so if we take a look at this equation, you can see that we already know Fu, we already know Fy. So basically we have like some strange variables in here. What is A and V? We have to find the net area in shear, we have to find the net area in tension, and we have to find the gross area in shear. So these are the three things you have to find to be able to solve for this equation. Now, let's find each one of these. So in here I have the whole shape. I take a top view for my wide flange, and I'll start with considering that the failure of the shear block would take place in here, as indicated already. So as you can see here, we have like, you can consider this as one piece, this is another piece. And also you have to consider that you have other pieces at the bottom. So the failure will take place in the top flange and the bottom flange. So if we calculate AGV, which is again the gross area in shear, what is the gross area in shear? It's basically whatever we have in shear over here, like if we consider one piece, one part from here, we can see that the shear will take place in over here, because if you have the force like this, the shear would be parallel to the applied force. So the distance from here to the end is equal to 200 millimeters. I'm taking that 200 millimeters and I'm multiplying it by the thickness of the flange, 39. Now, you're done with one part, but you have also another 4 parts. So you have this one, you have that one, and you have other parts from the bottom. So that's why I'm multiplying by 4. And overall, you would obtain your area in shear, gross area in shear, equal to 31,000 millimeters square. Now, if we continue and check for A and V, delete this. A and V is basically the net area in shear. Now, once you have found the gross in shear, you will subtract from the AGV the bolts that would fail. So again, how is that? You will consider the part where will be facing shear. So in brown arrows, we can see that here we have shear. We considered initially 200, but now we have to reduce it due to the fact that we have bolts in here. So from this side, we can see that the failure would take place in 1 bolt, 2 bolts, and a half bolt. So here we have 1, 2, and half bolts. Now, that 4 is appearing again. Why? Because, again, as I said before, we have 4 parts that are failing, this one, that one, and from the bottom. So I'm multiplying by 4. Also, I have 2.5. That 2.5 goes to the number of bolts that I'm losing. And also 26, which is basically the whole size, 22 plus 4. And lastly, the thickness of the flange, 39. So if you plug all these values in, you would obtain your net area in shear. Once you have the net area in shear, you can continue and find the net area in tension. So similar to what we had in shear, we have in tension. Now this part is going to be in tension. This part of this the part of the member is in tension in yellow arrows. So if we have to consider this one, we have this in the equation here. You can see 310 minus 200 minus 26. Now what's that? This is basically the distance from here until there. So how do you calculate that? You can easily calculate that. And also, after you calculate this distance, which is appearing over here, you will multiply it by the thickness to obtain an area. So there is something I have to mention actually. When I consider the length in here, let's assume that the length is equal to 100. 100 in here, and you have another part over there, should be equal to 100. Now, when I considered in my equation, I considered that the whole thing would be equal for 200. So basically, I'm calculating for the top part, and the bottom part would be multiplied by 2. All right. Now, the net area in tension, if you calculate all of this, would be equal to 6,552 millimeters square. Now, before I continue, I would like to ask you if you have any question over here, because this is important to understand. So, guys, if you have any question, please ask me now before we continue, if this is not clear.
At the beginning, why did we choose such a big area?
At the beginning, why did we choose such a big area? Yeah. Well, the reason is you're supposed to actually start close to that area, 21,000. That's a good question. So if we go back again here, AG minimum is found to be 21,000, right? Now, according to the question, it is we are supposed to check for HEA, HEB, and HEM. We have too many sections to check. So that is time consuming if we do it right now. Also, there is something you have to consider. Now, it is true that we have to satisfy this condition. The minimum area we have to consider is 21,000. But also there is something very important. Here you can see that the distance is given to us 200 millimeters. So you cannot pick any section that has less than 200 millimeters. You need a section that has wide flange or the width of the flange bigger than 200 millimeters. So you have to satisfy two conditions, this one and that one. And you will be checking. You will start obviously with a low value of AG minimum, and you will increase until you satisfy all the conditions. So it appears that I have a very high value for AG, but that's because I want to make the solution straightforward. Is it clear now? Yes. Now this is actually the section that satisfies our needs. Other sections would fail or might be too heavy. If you check the solution that is given to you in auto class, some sections would be okay. The only section that satisfies like safety and economy is HEM 300. So that goes through a lot of process. So is it clear why I have this big value of AG minimum or A gross that I chose?
Yes, Hocam, thank you.
You would. Any more questions, guys? I want to make sure that you actually understood the part of AGV, ANV, and ANT. Oh, it seems like it's clear. Okay, now we can proceed. Since we have found all of these, we can check our equation now for the block shear. So in this equation, we have to check at the beginning this part, and we have to check this part. Now you compare between both values. When you compare between both values, you have to pick the smallest value. Now, why is that? The smallest values shows you that actually how the failure would take place. Again, how is that? Now here you can see that there is Fy and Fu. In this equation, you can see that you have Fu and Fu. So if now for our condition, it appears that this equation shows is actually the smallest. And it tells us that actually the area in shear would yield and the area in tension would rupture. Now, if we consider if the case was that this part is the smallest, you will notice that it is saying to us that the part in shear would actually rupture. It will cut, totally cut, and the part in tension would totally cut also. So you have a separate piece. Now, since we have found out that this part is the smallest, the part on the right-hand side, okay, we have 10 minutes now. Guys, if this one finishes, please make sure you enter again using the same link provided. All right, so we have this equation. We check all the values now. We have 0.75 by LRFD. This is the factor of safety. 0.6 given to us. The yielding strength, the gross area and shear we found previously, plus 360 for FU. This one that appears is for UBS. UBS, you can take it as one to simplify the problem. And lastly, A and T, which we found previously. So if we check this equation, it appears that the capacity of this member for block shear is 5,068 kilonewtons. Again, it's bigger than 4,500. So in this case, we satisfied the gross yield, we satisfied the net rupture, and we satisfy the block shear. So all of these. And if you compared, let's say, HEM 300, HEM 100, whatever, let's say you have HEM 300, HEM 350. Both of them satisfy your requirements. So you have the safety is good. We have safety satisfied. Now we have to satisfy economy. So when you want to satisfy that, you have to consider the lightest weight member in between these two. Now, how do you do that? So if these two satisfy our safety condition, we have to check from the sections table. We have HEM 300, for example, here. It is given to us in the first column that the weight is equal to 238 kilograms per meter. And if we consider, okay, we don't have 350, let's consider 360. If also HEM 360 satisfies the safety, we have to check the weight. So we have 250 here, we have 238. Which one am I going to take? I'll take the lightest wide flange, of course. Why? Because it reduces the cost. So based on that, you make your decision and you pick your lightest and safest section. Now, okay, so we still have 7 minutes. Are you still with me, guys?
Yes, sir.
Okay. Do you have any questions about this problem?
Can you repeat the area for net tension, please?
The area for tension, okay. So for the area of tension, if you consider one side over here, I take that part and I have it in here. This is the part. Now you have to consider that whatever parallel, since this is your force P, whatever you have parallel to the force is considered to be shear. And it has to be parallel also to the section. And if it was parallel to the force, but perpendicular to the section, that is the tension force. So this is where you decide where is the tension, where is the shear. Now, once we understand that, we have to find this length from here until there. Now, if you find this length and multiply it by the thickness, you get your area. But now since we are talking about A and T, we want the net area and tension. So you have to exclude the parts of holes. Now, since we have half hole here, and you have another half hole in there, so I have tension in here, I have tension in there, I have half bolt going from there. So basically you have one bolt going from top side only. Now, if you find the distance from here to there and distance from here to there, how you find that? You basically given the wide flange width, you're given 200 for the distance between the bolts. So you can easily find these two distances. I'm assuming that is 200. It's not 200. We can check it fast now. Give me a second. Okay. Let me calculate this. So basically it's actually 310 minus 200, which is equal to 110. So this part is actually 55 millimeters, and that part is 55 millimeters, the whole thing. Now I'll write the equation again. A and T is equal to 55 multiplied by, okay, before we multiply, we have 55. We have to take into consideration that we have a loss of half bolt here, half bolt there. So it's actually one bolt. So minus 26, close the parenthesis, multiplied by the thickness of the flange, 39. And since I consider the top part, I have to consider the bottom part of the wide flange. So that's why I'm multiplying by 2. If you calculate this, you would obtain 6,552. Was it clear? If it wasn't clear, I'll repeat again.
That's okay, thank you.
You're welcome. Any more questions, guys? So always,
Hocam,
yeah.
can you return the please before this slide because I missed some parts.
Which one?
Before this slide.
This slide?
Yes, this one.
Do you have any question about it?
Okay, Hocam, thank you.
All right. Okay, so any more questions, guys? Okay, so I was saying, yeah.
Hocam, I guess you calculate the A and T wrong because the you calculate for just one side. This will be 110, not 55.
All right, let me check again. So 310 minus 200. Okay, 310 minus 200 would actually give you 110, right? But you have to divide over 2.
Why, hocam?
Let's make it clear. It's overcrowded. So why we are dividing by 2? Now you have this distance from here is 200. If you take 200 out of 310, what you obtain is actually these two distances, which are equal to 110. Now divide by 2, you obtain each side, 55, 55.
Okay.
So basically this is, all right, I got your point. So my mistake is here. Yes,
Yes.
totally right. This is 110. Thank you so much. All right, I assume we have everyone now. So let's continue with problem number 7. Now, in problem number 7, we have, for the tension member shown below, determine if the member is able to safely carry the applied loads. Given loads are service loads and factored loads, use LRFD and ASD load combinations separately and compare your findings and consider that the gusset plates are okay. All right, so we have given the size of bolts 20. We have the steel, we have the dead load given 150 kilonewtons, live load 250. And we have here the section. So we have a gusset plate in there. We are given the dimension of the gusset plate, so it's not a design problem, it's analysis. We have 3 bolts connected, and you have to consider that this shape is L shape. Even that if that wasn't given to you, L 150 by 150, you have to see it from the shape. How is that? From here, we can see that there is a leg for the L section. Well, since we understand the problem, we can proceed. We have to consider, first of all, the factored loads based on LRFD. So since I have a dead load and live load, first I will check for 1.4 dead load. It gives me 210. If I factor the load with this equation, it appears to be 580 kilonewtons. So for LRFD, I'm going to consider this. Now for the ASD, it appears to be different. We will consider 1DL dead load 150. If you consider the live load as well, it becomes 400 kilonewtons. So 580 for LRFD and 400 for ASD. Now from the section tables, the gross area for the L section given to us 150 by 150 and 12. Let's take a look. So if we take a look at L150, by 12, we have it over here. So as we can see, we have the gross area given to us 34.8. If you multiply it by 100, it becomes millimeters square. So this is what we have. Now we have to consider again, as before, we have to consider the gross yield, net rupture, and block shear. So first of all, we're starting with the gross yield with LRFD. So the equation that we always use, you plug in all the values and it appears that the value or the capacity of this member is 861 kilonewtons, bigger than the LRFD load, 580. This is good. If we check for the ASD case, now this time you multiply the gross area by Fy and divide by 1.67 and compare it this time, you will compare the capacity of this member by the load factor in ASD. So it appears that the capacity is bigger than the load combination, which is good. So the gross yield is fine. Now, if we consider the net rupture for this section, I have the equation again that we know. Fu by AE, we have to find U to be able to find the effective area. So what is U? If you check from this section, if you check from AIC, for case number 2, 1 minus X bar over L. So X bar, you can find it basically from the section tables. So again, if we go to section tables, 150 by 12, where's X bar? So for X bar, all right, so it appears to be this one, XS. Exactly. So XS is actually what we need, 4.12. And since this is symmetric, 150 by 150, so you can see that X is equal to Y. So it means that the centroid from this side to here and the centroid from this side to that side are equal. But notice something, it might be not this case, you might have this leg shorter than that one. You have to focus that you're taking the distance from where you have connection. So we have the bolts in here to the centroid. Now, once we have X bar, we have the distance from the first bolt to the last bolt, 120. We obtain our shear lag. Now, also there is something else that applies from the AIC table D, case number 8, single and double angles. So case number 8 actually applies for us. And here we have this condition with 3 fasteners per line in the direction of loading. And we actually have 3 bolts in line. So we have U given to us equal to 0.6. So I'm taking U 0.6. Which one am I supposed to pick? I pick the biggest one from case number 2. Now I continue and calculate the net area. So you're considering the gross area minus the number of holes that you're losing. You're losing 1 hole. The cut will be like this. So you're actually losing 1 hole. Okay, so minus 1 by the size of hole multiplied by the thickness. As we said before, it's 150 by 150 by 12. So the thickness is 12. And you obtain your net area. Multiply, you get your effective area. Once you get your effective area, you can calculate this equation according to LR of D. So this one is actually 430 multiplied by the effective area, multiplied by the reduction factor or factor of safety, and you get your capacity of member in net rupture 676, bigger than 580. This is good. If we check for ASD, now this time we divide by 2. So if you divide by 2, you will have 450 kilonewtons capacity according to ASD, and it is again bigger than the load combination with ASD 400. So this is good as well in net rupture. So until now we satisfy the gross yield and the net rupture. Now if we check for the block shear, similar to the problem we had before, now we have the block shear but different shape. We have L shape. Now we want to consider this equation again, and as we know, we have to find these 3, ANV, ANT, and AGV to be able to solve for this equation. So let's begin with AGV. This is very simple and straightforward. If you consider this failure that is happening in here, and take that part outside and sort of analyze it with all the dimensions. So in here, we have the force. So we have tension at this part in yellow arrows, and we would have a shear force in this part in brown arrows. Now, after understanding all of this, you can see that because of the failure, we would have 2.5 bolts that will be included in the failure. Now, if we calculate for the gross area in shear, we take the whole thing from here until there. This distance would be 180 multiplied by the thickness 12. So you got your AGV. If we consider the net area in shear, now it is going to be equal to the gross area in shear, this one, minus the reduction caused by holes of bolts. So 2.5, because we have 2.5 bolts, multiplied by the hole size, 20 plus 4, 24, multiplied by the thickness of this leg, which is 12 millimeters. You obtain your net area and shear, 1,440. We check for the net area and tension. Now this time I will consider the distance from here until there. This is the part which has tension, so I'm considering this side, 60 millimeters. multiplied by 12, the thickness, and you take into consideration that you have half a bolt that is reducing the capacity of the member, or actually in here. So this part is only in tension. This part of the hole will not take any force. So minus 0.5 half bolt multiplied by the size of the hole multiplied by the thickness. You get your net area in tension. We have all these values now, AGV, ANV, and ANT. We proceed and check for these two equations. Which one is going to be the smallest? If you plug in all the values, you will get that this one actually is the smallest. If you proceed and check according to LRFD, you will take the whole thing in here and multiply it by 0.75. So let me explain it. 0.6, we have it there, 275 for the yield of steel. We have AGV, gross shear, area and gross shear. We have 430 for FU, UBS, again I take it 1, and 576 for the net area and tension, this one. And lastly multiply by 0.75 because of LRFD reduction factor. You would get 453 kilonewtons as a capacity for the block shear. But this is less than what we need, 580 kilonewtons. So this is not good. Now, if we check for ASD, again, the same equation. Okay, I forgot here a parenthesis. We can close the parenthesis. But anyway, now if you take the whole equation again, divided by 2, you would get 302. Compare it to ASD load combination 400 kilonewtons, it is lower. So this is not good as well. So the member is expected, if you apply a load exceeding, for example, 580 kilonewtons, according to LRFD, we would face an issue that the member would fail in block shear. And if we consider Lmax, which is the maximum length that we can have for the member, let me go back again and show it to you. What is Lmax? So this is basically Lmax, the maximum length we can have for the member in tension. We have equation for that. Now, what's that equation? It is actually R minimum, the radius of gyration, multiplied by 300. This is just a value over there, it does not change. So what's R minimum? If you go back again to the section table, R minimum for 150 by 12. All right, so it's taken as 2.94. So yes, over here we have the R, the least value. If you compare RV, RX, RY, and you compare any other values given to you, you will find that this is the lowest radius of gyration. Now, since I have the lowest radius of gyration taken from this section table, I plug it in this equation and I obtain that the maximum length that I can have is 8.8 meters or 882 centimeters. So this is the Lmax. Now, if we think about how the block shear would happen, if we take a look at this photo in here, we have L section that is connected by 3 bolts, similar to what we have. And this is what actually the failure would look like. So this is the case for the block shear. Notice that this part was in tension and this part was in shear. So to conclude, the member is not safe as the capacity in block shear is lower than the load. So that's how we solve this question. Do you have any questions, guys, about this? Anything not clear? Okay, I assume that it is clear, unless someone speaks up. Okay, so going to problem 8 now. Check whether the tension member shown below is able to safely carry the applied loads. Use LRFD and ASD separately. Gusset plates and welded connections are okay. Calculate also the maximum length, Lmax, preferred for this tension member. So here we have RU given to us 1000 kilonewton as a factored load by LRFD. So you already have the load combination. And RA is 500 kilonewton for ASD load combination. Now, as you can see here, we have these two sections. This is a built-up section made by a C section or UPN. And we have IPN connected to it by weld from this part here. So you would have a built-up section overall. Now, since we are dealing with a built-up section, we have to find initially the gross area, because I want to check the yield in gross for the section. So if you take a look at the section table for UPN and IPN 100, you will get this area for that one and this area for that one. You basically sum them up, you get your AG total for the built-up section we have over here. Now, I can calculate the gross yield based on that. So basically, according to RFD, you multiply 0.9 by the yield, by the gross area, the total gross area for the built-up section. And seems like the capacity is 1060 kilonewtons, and it is bigger than 1000 kilonewtons according to LRFD load combination. So you do not compare it with ASD, since you multiply by 0.9 here. So this is fine according to LRFD. Now I want to consider the rupture. Now, since my connection is actually welded, I will make use of stable. Okay, so from here, it says that all members in tension, where the tension load is transmitted to some but not all of the cross-sectional element by fasteners or by longitudinal welds in combination with transverse welds. So weld actually goes in the case number 2. So that's why I'm taking this equation. 1 minus x bar over L. So if you calculate x bar for the built-up section, you will find that x bar is going to be equal to 29.63. Now I'm not showing how you actually find x bar, because you should be able to find it. Also, why did I take x bar from here, not from there? Well, the reason is that you have your weld over here. So you're taking the distance from this side to the centroid of the whole shape, not the other way around. So once you find your x bar, you have to consider the length. So we go back again to the problem. Which length am I taking? I'm taking this length. Similar to what we had in bolts, but this time we have a weld. So I'm taking the distance equal to 75 millimeters. Now, if you plug in all these values, you get your shear lag, 0.605. If you calculate the effective area, now since we have a weld, we don't have any reduction by bolts, and we don't have any cause of increase for the area by staggering. So for the welds case, you're basically multiplying AG, the gross area, by the reduction or the shear factor, U. Now, if you multiply all of this, you get your effective area, 2,589 millimeters square. And if you check for the equation according to LRFD, I'm not checking ASD in here to save time. So if you check for LRFD, you multiply by 0.75, multiplied by FU, this value 430, and lastly the effective area. If you plug in all these values, you would obtain the capacity of this member for the net rupture equal to 1,800, bigger than 1,000 kilonewton, again, bigger than the load in LRFD combination, because I multiply 0.75. I'm following LRFD. So this is good. I satisfy in gross yield and I satisfy in the rupture. Now, in the question, it is asking us one more thing. It is asking us to find the maximum length preferred for this tension member. So we will be using again the same equation we had before. L equal to R minimum multiplied by 300. Now, since we have a built-up section, you're supposed to find R minimum or radius of gyration by yourself. How you do that? You have the equation. You have to calculate for each member alone. For example, this one, you calculate moment of inertia. Let's say that this is your x-axis. This is x-axis and that one is y-axis. At the beginning, you find for this section, it's I, call it I1, moment of inertia. You find it in the x direction and you find it in the y direction. Call them I1x and I1y. And then you will find for UPN, you will check the moment of inertia about the x-axis and the y-axis. You can call it I2x and I2y. Now, when you consider, you will get Rx, which is equal to Ix total divided by AG, A gross for all the built-up section, and you will also calculate Ry, which is Iy total, which is basically the summation of I2y plus I1y. This would be your Iy total divided by everything under the square root divided by Ag. So you would obtain two values and you're supposed to pick the lowest or the minimum value. If you do that, you will obtain your R minimum equal to 3.19. And if you put that in the equation that we know, R minimum multiplied by 300, you will get that the maximum allowable length is 9.6 meters. So that's it for this question. Now I want to mention something. Sometimes we have this L max. Why we have a maximum length for a tension member? Well, because if you had a very long member in tension and you're not satisfying this condition L max, for example, you go, let's say 12 meters or you go 20 meters for the length of the tension member, you would face issues that the higher you go in length, the more vibrations that the member in tension would face. So we don't want any member in tension to be vibrating, and because of that, we limit the length of the member in this way. So that's it for this question or for the whole problem set. Do you have any questions, guys?
Hocam, can you go back to question 7's last slide?
Sure.
Actually, the previous one before this.
Okay.
I'll take a screenshot.
All right. Let me check. Yeah.
Okay, thank you.
You're welcome. Any more questions?
Hocam, are you going to upload the lessons?
I'm not going to upload anything.
All right.
I mean, because first of all, these problems you were supposed to solve them. Now, there is a difference between a student who cares about the course and attends and check the content, like you, all of you who are attending now, and there are people who don't really care. So whoever wants to learn more, they should attend and ask questions, interact. So to make it fair with everyone, I'm not sharing the documents. Any more questions, guys? All right, so assume we are done. We are actually done with tension members. So next Friday, hopefully we'll continue with members in compression. which is problem set number 2. I hope that you take a look at problem set number 2. Try to solve problems. When you try to solve problems and get into this recitation, you will be able to ask questions and see where are your weaknesses. You can understand better. So try your best to solve some problems from that problem set number 2. Thank you all for attending again, and see you next week. Have a nice weekend, everyone.
Thank you, hocam.
Thank you. Bye-bye.
Thank you hocam.